Okay, so what we're going to do is to start doing some various concepts in probability. So what I want to talk about is the joint probability density function. When you think of joint probability densities, you've got several variables going on, and you want to figure out what's the probability, say, x takes on this value and y takes on that value. Which class do you think might be useful for stuff like this? Which previous class of yours?
Stat 201.
Not Stat 201. Where might have you seen things with several variables? Multi-variable calculus, right? There's a reason this is a prerequisite for this course. So in some sense, what you would want to be able to do is deal with functions of several variables. This leads to the change of variable formula, which is either done and hated or not done at all in standard multi-variable calculus classes. I will show you ways to bypass the change of variable formula in many cases we need. And so we will not need to go fully into all the stuff in multi-variable calculus. What I want to do now is I'm going to consider 2 coins. Oh, sorry, I think I'm going to consider 5 coins. And in this case over here, I'm doing the joint density. So x is the number of heads in first 3 tosses, and y is the number of heads in the last 2. And I'm going to have the same thing here. Okay. If you look at these, do they have the same joint density? Is the probability of getting x equals 2 and y equals 1 the same here as it is here? Okay, so we can just quickly look and see there's at least one cell where they differ. Okay? Let's add up the first row. So if we add up the first row, what do we get?
1/8.
Okay, we get 4 over 32, which is 1/8. If we add up the second row, 3/8. Next row, it's the same thing, so 3/8. And the last row, 1/8. And if we add the columns, 3, 6, 7, 8, we get 1/4. Over here we would get 1/4. 12, 13, 14, 15, 16, we would get 1/2. So if you look at this, if I add up just the first row, that's telling me what is the probability that x equals 0, and I don't care what value y takes on. If I add up the stuff in the first column, I get what's the probability that y takes on the value 0, and I don't care what value x takes on. So this leads to the marginal density functions. So I start off with a joint probability density function. I start off by specifying all the different pairs of x and y, and I tell you how likely each pair is. And if I know how likely each pair is, I can then figure out how likely it is for one value, for one of the variables, x to take on a value, by just integrating out or summing out the other variable. If all I care about is x equals 0, I take x equals 0 and I sum over all possible values of y. Not surprisingly, if I add up all these numbers, what do I get? 1. This tells me the probability x is 0, the probability x is 1, the probability x is 2, the probability x is 3. Well, if x is the number of heads in the first 3 tosses, it's going to be a 0, 1, 2, or 3. So if I sum these 3 values, I have to get 1. What would I get if I sum these 3 values down? I'm sorry, these 4 values. If I sum these 3 values down here, what would I get? I would get 1. A quick way to prove that this has to be 1 is these numbers here represent summing everything by rows and then summing all the rows. That means I've summed every element. If I look down here, I'm first summing in columns and then I'm summing all the columns. I'm still summing every element exactly once. So these also have to sum to 1 as soon as I know that these sum to 1. They also sum to 1 on just probabilistic grounds that this is the probability y is 0, this is the probability y is 1, this is the probability y is 2. Those are the only possible values for y. It has to sum to 0. Now let's come over here and let's look at these values. What do I get if I sum the first row? 1/8. The next one should be 3/8, 3/8, and then 1/8. And if I go down, I should get 1/4, 1/2, and then 1/4. Yes?
The box in the last column, or the second one down in the last column, shouldn't that be 116?
Which one?
The 2 up from that one.
This one?
No,
This one?
Yeah, that one. Just because they're not adding up right.
Okay, probably 1/16. I might have just typed it wrong. So I think you found a mistake in my book. Excellent. So that should be 1/16, yes. Okay. There's a lot we can deduce from this. When I give you a joint probability density function, I'm telling you what's the probability you get a pair, that you get the value x equals this and y equals this. When I'm calculating the marginals, I'm integrating out one of the variables and I'm looking at just the other one. Over here, if you look at the marginals for y, it's 1/4, 1/2, 1/4. It's the same as the marginals we get here, 1/4, 1/2, 1/4. And the same for x's. So we have a wonderful negative theorem here. If I tell you the marginals of x and the marginals of y, does that uniquely specify the joint probability density function? No. Here's an example. So the joint probability density function is more complicated than the marginals. You can get the marginals from the joint probability density function, but knowing the marginals does not uniquely specify what's going on. This is a much nicer example to look at the first one. We have this wonderful property that if you look at this number 6/32, this is the same as 1/2 times 3/8. So 1/2 times 3/8 is 3/16, which doubles to 6/32. Let's choose another one. 1/32 is 1/4 times 1/8. If you go through, there's not that many to check. Each cell here is the product of these two. If the joint probability density function factors as to a function of the first variable times a function of the second, then the variables are independent. So if you think about it, if I have my density function for x and my density function for y, and they don't interact at all, if they're independent, if I want to know what's the probability x takes on its value and y takes on their value, you just multiply the two products. So one way you can tell if two random variables are independent is to just go through and see, is the joint density function the product of the two density functions? So you can calculate the modules and just see, does that work? In this case, are these variables independent? Which cell do you want to look at just so they're not independent? Yes?
One of the zeros.
Yeah, one of the zeros, right? I don't want to try to figure out is 3/16 1/2 times 3/8. It's been a long, long set of flights. 0, that's much easier. I don't care what this is. This is not 0, this is not 0, their product can't be 0. So this is not independent. What I've done here is I believe I've glued the first head and the fourth head together. Let me double check and make sure that's what I did. The first and fourth coins are glued together. First and fourth coins are glued. So they're like this. So they're either both heads, that's a half drawing, or they're both tails. Question?
Isn't that the same as just flipping four coins?
It is. But I can view this as your coin 1 and coin 4. And so their values are dependent. Now, in this case, the dependence is terrific. If I know the value of the first coin, do I know the value of the fourth coin? Yes. If I know the value of the first, if I know the value of x, do I know the value of y? No. There's some correlation between knowing x and knowing y. If I know x equals 0, what do I know about y? So if x is 0, what do I know about y?
It's not 2.
It's not 2. Because the only way I could have a 2 is if both coins, 4 and 5, ended up as heads. As soon as I know x is 0, I know coin 1 has to be a tail, so coin 4 has to be a tail. If unfortunately I know x equals 2, it's more complicated as, all values of y are still possible. So you can clearly see that there are some dependencies here. And so the main idea in terms of what we want to do is we want to look at a joint probability density function. So we'll have maybe f of xy or f of x1 through xn. And then we have the marginal density functions. And so what I can do is maybe f of x1 of x1 plus would be the integral x2 goes from minus infinity to infinity, dot dot dot, integral xn goes from minus infinity to infinity, f of x1, x2, xn, dx2, dxn. And of course you would have similar things for sums. And if I want to find the marginal density function of x2, I would have x1 go from minus infinity to infinity, then I would have x3 go from minus infinity to infinity. So what I'm basically saying is integrate out all the other variables and keep the first one fixed at x1, and that will give you the probability density function for x1. And then the variables are independent if the joint probability density function factors. So that would mean f of x1 through xn can be written as f, say x1 of x1, dot dot dot, f of xn of xn. Does this look like a pleasant or unpleasant integral to do? Unpleasant. Okay? If this does not look unpleasant, see me, you're having issues. Okay? You should not be happy about having to integrate this. This should be bringing back horrible, horrible possible integrals from Calc 3. Then you go, oh god, maybe I can use spherical coordinates, or maybe cylindrical, or maybe some kind of special coordinates. Oh, but I'm only going to be integrating over some of them. This could be a nightmare. If this is true, you've reduced it to a bunch of Calc 1 problems. Now, in the special case when things factor, I can then write this integral as the integral of f of x2 dx2, integral of f of x3 dx3, integral of f of x4 dx4. What do all those integrals equal? What do I get if I integrate f of x2 from minus infinity to infinity? 1. So if they all factor, it's really easy to see what happens. The f of x1 just comes outside the integration. Then when I integrate over x2, I get 1. When I integrate over x3, I get 1. When I integrate over x4, I get 1. Okay. Any questions about what we have here? So I go through a little bit more detail in the book. We're not going to do an enormous amount with bad joint density functions, but we need to be aware of them. Okay? It is not surprising that when things factor, it's going to be significantly easier. In the real world, do things always factor? No. That's why God created advanced probability classes or advanced statistics classes, where you can really go into what happens in those situations. I want you to be aware of the issues right now. What's particularly nice, though, is there are some quantities that we are going to study that are actually nice even when things don't factor. The mean, it turns out, is going to be very nice. The expected value of a sum is the sum of the expected values. We'll hopefully prove that today. It is not the case for variances. And so variance calculations become a lot harder. I will give you another problem to think about over the weekend. How many of you have ever had like boxes where you're opening the box to get a prize? Okay. I was recently with the kids, we were at McDonald's. My son got the same prize 3 times in a row, and my daughter also got that prize once. My son was not too happy. We actually talked to the manager, and he was able to exchange and give him another toy. So here's an interesting question. Let's say you have C toys, and each toy is equally likely to be in a box, and each box has only 1 toy. You're not going to be lucky to get 3 toys in a box. How many boxes do you think you need before you get every toy? This is a very complicated problem, and I'll email you the full description, the full statement of the problem. This is a very complicated problem. We'll hopefully solve it on Monday and show how you can use the techniques we're doing to attack problems like this. Now, the fluctuations in terms of how many boxes you need, that's going to be a lot harder. But just calculating the mean number of boxes is not so bad. This is why the expected value of a sum is the sum of the expected values, this linearity of expectation that we're going up for today. It allows you to solve a whole variety of problems you care about. And trust me, if you have kids, this is a big deal, okay? My son actually wanted us to keep going to McDonald's to see if he would continue to get the same toy again and again and again. And I will admit I was tempted to go to McDonald's 3 times one day just to see, how long will this hold? As an aside, do you think it's a reasonable assumption that all toys are equally likely? Why not?
Because some toys are cheaper to make than others, so those are probably the ones that are more likely
No.
to get.
If kids know that they're missing one toy, they're gonna come back.
If kids know they're missing one toy, they're going to want to keep coming back. You don't want the kids to get too frustrated, but you do want them to keep coming back and advocating. And so the question is, it's an interesting probability question. What should be your probabilities of the toys in the boxes? Which one should you produce more of? So I'll leave that as an advanced thing for you guys to ponder. All right, so what I want to talk about now is convolutions. So say we have x and y with densities f of x, f of y, and independent. So a lot of mathematics boils down to the following. You want to understand something simple and then build more complicated things out of that. So if I know my random variables x and y, can I figure out what is the density of x plus y? We've talked earlier that if x and y are dependent, the answer could be anything. I could have y equals negative x, I could have y equals x. But we didn't write down the answer if x and y are independent, correct? We have not done that yet, correct? So let's calculate this. So we're going to let z equal x plus y. And we want to calculate its density. What I like about this is this goes back to the same ideas you've seen in Calc 1 when you want to prove all the derivative laws. How do you prove the derivative of a product? How do you prove the derivative of a sum? You always go back to the definition of the derivative. So how do we do things here? Let's look at the cumulative distribution function. Big F of z of little z, it's the probability that big Z is at most little z. And then if we take the derivative of this, that'll give us the probability density. Okay? So how do I do this? Well, I'm going to have an integral. I have my density function fx of x, fy of y, let's say dy dx. So x can range from minus infinity to infinity, and y can range from minus infinity to what? How high can y go?
Z minus x.
Z minus x. Because we know x plus y has to be at most z. So the region I'm integrating here over is going to be y goes up to z minus x for a fixed value of x. Okay. Because these functions integrate to 1 and they're non-negative, I don't have to worry about justifying anything I'm doing. I'm only working with positive numbers. One of the great things in pure mathematics is we just write down symbols. Does anybody know what function is the antiderivative of little f of y?
Big F.
Big F of y. Right? So we have, this is the integral, x goes from minus infinity to infinity, fx of x, and then we get big F of y at z minus x minus big F of y at minus infinity dx. And what's big F of y at minus infinity? Zero. It's a cumulative distribution function, so this is just 0. Alright, so this is big F z of z. So I now want to take the derivative. But when I take the derivative, and this we've got to be a little bit careful about, what would you love to do? What am I taking the derivative with respect to? What is my variable? Z. I'm not taking the derivative with respect to x. X is my dummy variable of integration. I take the derivative with respect to z. And essentially, because everything here is nice and positive, I can pass the differentiation inside the integral. And the derivative of the integral is the integral of the derivative. You'll prove this really rigorously in an analysis class. For now, I hope you think this is reasonable. If you want more details, I'm happy to provide more details. So let's pass the differentiation inside. What's the derivative of big Fy of z minus x? So I want the derivative of this.
It's little f.
It's little f. And then I have to take the derivative of z minus x with respect to z. What's the derivative of z minus x with respect to z?
1.
1. So I can actually then immediately drop that. But this is the chain rule. So hopefully you've seen something like this before in calculus classes. What's wonderful is we never actually need to use big F of y. We only need to use little f of y, which is what we're given. And at the end of the day, we have an expression. So this gives us the value of little z. If you want, I'm going to justify this formula another way. I want to calculate what's the probability x plus y equals z. Well, if x takes on the value of little x, if I want it to equal z, what value does y have to take on? It has to take on z minus x. Because that way their sum will be z. And as I integrate this over all possible values of x, that's looking at all possible pairs that give us z. This is such an important relation that we actually give this function a name. We're going to use a special star. And I'll write it again on the next board. So this is called the convolution. So f convolved with g at x is going to be the integral t goes from minus infinity to infinity f of t g of x minus t dt. In this class, we are only going to be doing this when f and g are densities. When f and g are densities, it's much easier to justify everything that's going on. A lot of what I'm going to show you is true in greater generality. Okay. This is a new operation. How many of you have seen this convolution operation at some point in your life? Okay, excellent. This is a wonderful way to create a new function from old functions. Now the question is, as soon as you see a process that generates new functions, you want to ask, what kind of properties does this process have? So this is f star of g of x. What might you wonder about f star of g? Yes?
If it commutes.
If it commutes, does this equal g star f of x? And the answer is yes. Okay, so the question is, does it matter? Question? Okay. So does it matter which order we convolve? Does it matter if we have f of t g of x minus t or g of t f of x minus t? One way to prove that it doesn't matter is to do a change of variables. This is the boring, unenlightening method of proof, which I don't like. But it works, it gives you the answer. So go through here, do a change of variables. So you can change variables. There's a better way of doing this because we're taking a probability class. What does f star g represent? F star g is the density of, say, x plus y. What's g star f? The density of y plus x. Is addition commutative? Yes. These are equal as addition is commutative. So because addition is commutative, we know that f star g must be the same as g star f. If we were to look at a more general case where we just had two functions f and g, and they weren't probability densities, we wouldn't have this physical interpretation anymore. And then the result would no longer follow from this argument. It's still true, but we couldn't use this argument. But because we're in the very special situation that we have f and g are the densities, we have this wonderful interpretation. Okay? What do you think the next question I might ask? This will all be extremely important later when we get to the central limit there. This is the best, I think, for its swiveling so far. What might be next? So we've just shown f star g is g star f. We've dealt with sums of two random variables. What do you think would come next? Is it associative? What if I have three random variables? What if I have f star g star h versus f star g star h? What do you think? Equal or unequal? No, I'm seeing, I think that's a smile, but and a strong head shake. So do we agree that they should be equal? What's the interpretation here? The interpretation is this is x plus y plus z, and this is the density. On this side, it's x plus y plus z, and this is the density. And these are equal because addition is commutative. Oh, addition is associative. Wonderful. Let's do another problem. What do you think this equals? F star g at x. And I'm going to integrate x goes from minus infinity to infinity. What should that equal? 1. Why does it equal 1?
Because f star g is the density of some.
F star g is the density of a random variable. What is the integral of a density of a random variable? 1. If you give me a specific value for f star g and you ask me to do this integral, there's a good chance I'll do it wrong. Because then I might try to actually do the integral. Right? And if it's a really complicated integral, quite likely I'll make an algebra mistake. You know, I don't have that much faith in myself. However, if you tell me it's a probability density and ask me to evaluate its integral, I can do that without thinking. It has to integrate to 1. Now what this also means is it means if we integrate x goes from minus infinity to infinity, and then t goes from minus infinity to infinity of f of t, g of x minus t, dt dx, this has to equal 1. So we should be able to prove this directly from looking at the integration. When you have a double integral, this goes back now to your Calc 2 days, so I'll write the integral a little bit higher. So when you have a double integral, what kind of tricks can you do to evaluate it? How can you evaluate a double integral? What's the main trick we know? There's change a variable and there's something else. Can't be anything too involved because I'm not telling you what f and g are. It's got to be a very general thing.
Can you just switch?
You can switch the order. So you have to be able to justify. I'll send you the video when Kim was 2 how he learned to justify switching. He has a magic bubble wand. He just waves his wand. It allows him to switch orders of integration. Works in physics, works in economics, very nice. In math, we have big things like the Fubini theorem. And we have to worry about, are we allowed to switch the order of integration? It turns out if the integral of the absolute value is finite, then you can interchange. Well, the integral of the absolute value here is not going to be a problem, because these functions are non-negative. So switch orders. So we have, it's going to equal the integral t goes from minus infinity to infinity, the integral x goes from minus infinity to infinity, f of t g of x minus t dx dt. The reason this is so nice is we can now pull the f of t outside the integral. And we're left with an x integral. Well, look at this. I mean, I've got a translation g of x minus t. I could change variables if I wanted. This is the integral t goes from minus infinity to infinity, f of t. And I've got the integral x goes from minus infinity to infinity, g of x minus t dx dt. What does this integral equal? What's this integral equal?
Big G.
It would be big G at infinity minus t, then minus big G at negative infinity minus t. But we can actually do a little bit better than saying big G.
1.
1. Why does this integral equal 1?
Here, shifting PDF.
So I'm basically just shifting a PDF. I'm still going over the entire range of the random variable. If I integrate a probability density function, it's 1. So when in doubt, if I ever ask you an integral, it's either the capital letter associated to the thing, or it's 1. If you want to do this another way, you could say, let's let u equal x minus t, then du would be dx, and then x going from minus infinity to infinity is u going from minus infinity to infinity. And then this integral becomes the integral u goes from minus infinity to infinity, g of u, and this is why I have g here, not f, du, which is 1. So this integral is just 1. Now I'm left with integrating f of t dt from negative infinity to infinity. What's that integral? 1. So we've now given two different proofs of the convolution result. One of them is by doing a lot of integration. The other one is by saying it's got to be a density function, therefore it has to integrate to 1. I prefer the observation that it has to be a density function. We're going to see a lot of proofs by grouping throughout the semester. This is one of the key techniques. And again, as you go higher and higher in your math and stats, you want to learn which methods can you use time and time again fruitfully. This idea of having a story to tell, being able to interpret, we saw this with all the combinatorics we did. There's a reason we spent a lot of time doing the combinatorics in the beginning. It's preparing us for proofs by story. And that's what we just did. We were able to interpret what we were doing as a story. So if we were trying to do these convolutions, we can interpret it as summing independent random variables. Okay. Any questions on convolutions? Okay, what I want to do now is I want to go and do expected values, and I want to talk about the linearity of the mean. Okay, there's a lot of different ways to do this calculation. And so the idea is x1, xn are random variables, g1 through gn are nice functions. The expected value of a1 g1 of x, 1, plus what they got, plus an gn of xn, is the expected value, is a1 expected value of g1 of x1, plus yada yada yada, plus an expected value of g of xn. So the expected value of the sum is the sum of the expected values. We can even change things a little bit. We can take some kind of linear combination. We think back to linear algebra. We can even put different functions. So when we get to variances, we might want to be squaring some things. The question is, how do we prove this? The proofs always come back to the definition. So there's going to be a lot of integration here. And when you do a problem like this, you want to make sure that you don't overload yourself on notation. I claim that if we can do it for just 2, we can do it for 3 or 4 or 5. we can basically just group things. And really, if we can do it when all the g's are just the identity function, so g of x1 is x1, g2 of x2 is x2, we can do it more generally. So I'm only going to prove the expected value of x plus y is the expected value of x plus the expected value of y. If we can prove that case, the other ones follow similarly. In fact, one way to see these things follow similarly is if I have the expected value of x plus y plus z, how should I view that?
X plus y.
As I should view this as x plus y. And if I do a grouping like this, if I do it as the expected value of x plus y quantity plus z, this then would become the expected value of x plus y plus the expected value of z. And then we could expand that out. So at least in the case when I don't have any g's, I can do any sum if I can just do 2. This is very similar to what you've seen in calculus. If you can prove the derivative of a sum is the sum of the derivatives, you have it for the sum of 3 functions, or 4 functions, or 5 functions. Okay. What do you think would be a really nice assumption to have about the x's? They're independent. So as a nice exercise, go through and try to do the proof in this special case when x and y are independent. We're going to do the more general case. So we're going to let so the x equals x1 plus x2. And I'm going to try to avoid using x1 and x2 are independent. Okay? So let's calculate the expected value of x. By definition, this is the integral x goes from minus infinity to infinity of x times the density function of x dx. Okay? What did we do in the first part of class today? A long time ago, I know. What did we start off today by doing?
Joint distribution.
Joint distributions. This is a really good time now to use a joint distribution. What is the density function of my random variable being x? This is the same as x goes from minus infinity to infinity, x. Now I have some dummy variable, t goes from minus infinity to infinity, and I'll put the 2 subscripts, f of x1, x2. If the first variable is t, what does the second variable have to be?
X minus 2.
X minus t. And I integrate over all t, and I have an integral of x. So I'm just using the joint density function. Joint probability density function. Now you can see why things might be nice if this split. And you can change variables and do a bunch of things. Alright, it turns out we fortunately do not need it to split. Instead of using t, might there be a better letter to use? So by now, we're deep enough in the semester, you should know I love notation. I want notation that's clear and easy to look at, and really reminds me of what's going on. Do I want to use t for the first component? Or is there something else I'd rather use?
x1.
I'd rather use x1. You know, I can use t, but I think it's actually much nicer to use an x1. Good notation suggests what to do. If I have an x1 here, what would I love to have here?
x2.
An x2. So let's change variables. So we've got to be a little bit careful as to how we do things. So let's say x minus, oh, it should be x1 now. X minus x1 equals x2. Therefore, x2 Therefore, x equals x1 plus x2. Dx is going to be dx2. Am I allowed to do this substitution and change x to go from, to replace x with x2? What do you think? Seems reasonable. Why don't I just let x2 be x minus x1? Yes?
You don't know how x1 or x2 depend on each other.
Well, x1 and, x1 is ranging freely from minus infinity to infinity. The dependence is coming in the joint probability density function. But I think there is a small issue here. And the issue is I've now integrated out x1. x1 is now gone at this point, and now I have x over here. I really want to switch the orders of integration first. And have x1 go from minus infinity to infinity. And then have x go from negative infinity to infinity. And then for given value of x1, do this change of variable. So you've got to be careful. If at this point I've integrated out x1, x1 is gone. And now in terms of writing x minus x1 equals x2, x1's been integrated out. So I want to switch orders first. So it's the integral x1 goes from minus infinity to infinity. The integral x goes from minus infinity to infinity of x, f, x1, x2, x1, x minus x1, dx, dx1. Now in this situation, now I can make the change of variables. I fix an x1, and since x1 is fixed, x1 is not varying, now I can let x minus x1 equal x2. Okay? So the order in which we do things does matter. Okay. And so now, we get the following. So this is going to equal the integral x1 goes from minus infinity to infinity. The integral x2 goes from minus infinity to infinity. What does x equal?
x1 plus x2.
x1 plus x2, which is exactly what we're trying to get. We're trying to get the expected value of x1 plus x2. We now have an x1 plus x2. This is a good sign. And now we have f x1, x2, x1, x2, dx2, dx1. Okay? When you see an integral like this, what do you want to do to this integral?
Split it up.
Split it up. And so when we split it up, we're going to split it up into two pieces. We're going to have the integral x1 goes from minus infinity to infinity. And I'm going to write it this way, x1, integral x2 goes from minus infinity to infinity of f x1, x2, x1, x2, dx2, dx1. So for the first piece, I just have, well, look, I'm integrating over x2. I can pull the x1 outside the integration. Right? For the second one, I'm going to have an x1. I'm going to have an x2. I want to pull that outside the integration. Can I pull the x2 outside of an x2 integral? No. What do I need to do first? What do I need to do if I want to pull the x2 outside of an integral?
Switch the order.
Switch. So first, for the next one, I switch the order of the x1 and x2 integral, and then I can pull the x2 out. And then the second one is going to be plus an integral x2 goes from minus infinity to infinity, x2, integral x1 goes from minus infinity to infinity, f x1, x2, x1, x2, dx1, dx2. We are almost done. We want to evaluate the first integral. What is the integral over here when I go x2 goes from minus infinity to infinity?
Marginal x1.
The marginal density of x1. What we're doing is we're fixing the value of x1 to be x1, and then we integrate over all possible values of x2. That's the marginal density function of x1. On the second one, we fix the value of x2, and then we integrate over all values of x1. So what we're left with is the integral, we're almost done. x1 goes from minus infinity to infinity. x1 times the density of x1 dx1 plus the integral x2 goes from minus infinity to infinity. x2 f of x2 dx2. What's the integral of x1 times the density of x1?
The expected value.
It's just the expected value of x1. And similarly, the next one is just going to be the expected value of x2. Things would not have been much easier if we had the density function factored. Be a little bit easier maybe, but it's essentially the same proof. So we're finally doing some dividends of Calc 3 without having to work with specific functions. So what we're really using here is just general integration theory on R2. And now we have the expected value of a sum is the sum of the expected values. This is why the mean is such a nice concept to look at. The mean is linear. The variance is going to be much harder. The variance measures fluctuations. That's going to involve squaring. It's going to be a lot worse. Okay, any questions on what we've done up till here? Okay. So, we've got about 1 minute left. I'm trying to think if there's anything that is worth saying in just 1 minute. Probably not. So I think this is just a good place to stop and recap. So we've done a lot of calculations today. It's a good idea if you're uncomfortable with this, go over the book, talk to me, make sure you really understand what's going on. This is applications of multivariable calculus. In actual problems now, you would have to evaluate these intervals. And so a lot of what we're going to do is ways to bypass evaluating these intervals. Have a good mountain day. Remember, there is one free homework problem exemption if you climb the mountain.